It's a pleasure to have you here today. So Catalina did her bachelor's in physics with a major in astronomy at the University of Valparaiso. And she stayed on there with Professor Michelle Curry and did her PhD looking at BE stars, both the absorption and the emission lines. She created the BESOS catalog and still is working to expand that and look at correlations between the disk phase and the star. Currently, she's a professor at the University of Valparaiso, and we are delighted that she's here to talk to us today. I also have to say that I was privileged to have Catalina visit me in Canada when she was a doctoral student. She came for, I think, 3 or 4 months.
4 months.
4 months. You would have stayed longer, but you were worried about the February weather getting really cold. So, but I remember from our visit, it was lovely to have you there. And I also remember going skating, and I've never seen anybody, never been on skates before, just immediately take off. So anyway, back to the BE star research. So I'll let you take it away, Catalina, and thank you for joining us today.
Thank you, Carol, for the introduction. So I am going to share my screen. And now the presenting mode. No, it's not working yet. Now, are you looking the first slide?
Yep, we see your title slide. It looks perfect.
Okay, very good. So I'm going to start. So this long-term variability in B star, in fact, is a title for my own research that I awarded from the financial support from the government of Chile, and also is in the frames of the Poems project. So there is a lot of people here from that project also. Also, I want to say that I awarded the fund like 3 years ago, just when the pandemic situation started. So it was a very bad because I have a lot of money to travel, I go to conference and to collaboration, but it is okay. So this is my 3rd year of this project. So I imagine that all of you know what is a B star. Anyway, I will start giving a context for classical B stars. Yeah, there is a pointer here, I think. No. Just give me laser pointer. Yeah, no. Okay, so here, for example, you have different pictures for different structure of this in the universe that you can find at different scales. For example, you have here young stellar object, galaxies, AGNs, binary system. So all of these objects has in common that they have an accretion disk. So you have the central object and the accretion disk. Okay, and the theory that explains this accretion disk, how form and maintain, is was given by Chakura and Sunjaev in 1973, and they use the viscosity as the main mechanisms to create the disk. So what I say this because, for example, you have a lot of structure that have this accretion disk, but the B star are the unique in the universe that shows a decretion disk, so the opposite one. Okay, I can, yeah, no, okay. So, for example, that is the attractive part of the B disk, because you have the central star, and there is something happened to the star that turn on a mechanism and start to feed the disk with mass loss rate, and then you have this decretion disk around the star. So the first definition for a B star was proposed or was given by Collins in 1987, and he described it as a hot, massive star, non-supergiant, whose spectrum has or had at some time one or more Valmer lines in emission. So now we know that this is not the only definition, because we know more properties of B star, and thanks to observation and other techniques, we know that B star has a equatorial disk, for example, that is rotating in a Keplerian way, and also is very thin and optically thick. So we know that there is other system that also show, for example, emission in H alpha. So this is not the only definition. So a V star, we know that the E comes from emission that we can observe in hydrogen lines. In the optical, for example, we see it in the Balmer lines, in H alpha, for example. So just studying H alpha, we can know, for example, some general features of E disk. Okay, so what is the main question on V stars is that we know, for example, a lot of features of them, rotations, non-radial pulsation, binary system, etc. But we don't know what is the mechanisms that turn on the mass loss rate in order to create this degradation disk. So that is the big question that we are trying to answer in general. Okay, so some general features of V star is that we know that they are massive stars, so they are located here in this part of the HR diagram. So they are very luminous and the effective temperature is very high also. We know that the mass loss rate is in the order of 10 to the minus 6 solar mass per year, for example. And if we compare with the sun is 10 to the minus 14, so it's a lot of difference. Also, we know that the final stage of a massive star is a supernova explosion, so also is contributing chemically and dynamically to the interstellar medium. So there is very important try to understand the evolution of this star in order to quantify the contribution to the host galaxy, for example. Okay, so here I am showing different features of V star. For example, we know that they rotate very fast. The rotation is about 70 to 80% of the critical rotation. And also due to this fast rotation, the star changes the geometry. So for example, the equatorial radius is larger and the polar radius is shorter. And for that reason, here we have a higher effective temperature because it's close to the center of the star. And here we have lower effective temperature. So we can see a difference of temperature between the pole and the equator. Also, due to this fast rotation here at the equator, we will have a lower effective gravity. So then if we combine maybe this fast rotation with another mechanisms as non-radial pulsation, for example, then we can form an inner disk, for example, okay? Other thing is that we know that they have or they present non-radial pulsations. Also, we know that because they are massive star, they have a very high mass loss rate. And also, we know that 1/3 of the galactic V star are in binary system. So each mechanism by itself is not reproducing a degradation disk, but if we mix some mechanisms, maybe we can do it. Okay, so now all the theoretical people is trying to reproduce an degradation disk using a combination of these mechanisms. Okay, so okay, some observational features. For example, we see in the spectral energy distribution of V star. So here we have the photometric data in the red triangles, and in blue we have a Kurux model for this star. So it is the best fit for this star. So we can see that in the infrared part of the SED, there is an excess. Okay, so this starts in the near infrared part and can go from radio. So we can see that this infrared continuum excess is because there is different emission process occurring in the disk. Also, we know that they present linear polarization. And a recent work from Clement in 2019. They studied 57 targets, and they found, for example, that they have a lot of photometric data from the infrared, optical, and radio data, and they found that the radio data has a different slope in comparison with the infrared data. So they see that there is a turn down of the SED in the radio part. And the explanation for this is that the most possible explanation is that maybe there is a companion that is truncated the disk. Okay, so for example, they analyzed in the sample, they found that 26 have or show this turn down, and the others, in fact, there is not, they are inconclusive. So maybe the title of the work of they propose is that maybe all B stars has a closed binary, for example. Anyway, in a recent work that we submitted just a few months ago with the UB group in the university, we propose another mechanisms to have this turned down, okay? So, other thing that we usually see, we have variability at different time scales. For example, we have variability in the time scale of hours. So this is related to non-radiant pulsation. So you can see, for example, some features in the line profile. And also you have variability in the order of month. And this is, you can observe it if you have the emission line that is, you have two peaks, and the violet and red peak are changing constantly. So here, for example, you can see that it's explaining because there is an overdensity in one part of the disk. So this overdensity is moving with the disk. So when the overdensity is moving away, you can see the red peak higher, and when it's moving forward to us, you can see the violet peak that is higher intensity. Okay, so this model is called one-armed overdensity model, and you can see that the variation is in order of month. And the third term scale of variation is when you have the formation and dissipation of the disk. So here, for example, you can find H alpha in absorption, and then from this absorption is going to an emission. And that means that you have in the first part, you don't have a disk, so it's non-active phase. And then the disk is forming, so you have the active phase, okay? So if you study, for example, different epochs for a B star, and you see the cycle of the H alpha line, then you can obtain, for example, these parameters for the formation of the disk, okay? And this is in the order of years or month also. Okay, so thanks to interferometric technique and also spectroscopy observation, now we know that we can obtain information about the geometry, cinematics, and dynamics of the disk. So we know, for example, that BDs are very thin and they show an open angle. So we have a flaring disk, and this higher scale is given by this equation. So for example, if you consider that the temperature of the disk is similar to the temperature of the star, then you are going to obtain an open angle of 10 degrees, for example, and it's occurring here at 3 times the stellar radius from the equator, for example. Okay, also using, for example, different observation in different wavelength range, you can obtain different size. So for example, if you observe in the optical range and you calculate the emission region in H alpha, then you are going to obtain a higher size of the disk. But if you move to the infrared, you are going to obtain shorter size of the disk. And this is because you are looking close to the star. Okay, so depending what you want to, what do you want to study, you are doing different observation in different range. Okay, so we know the future that I already say about V start, but we don't know the mechanisms to form the disk. But when the material is already in orbit, then the best description for the disk is the viscous degradation disk model. Okay, this is the most accepted theory and also is observational work. Okay. So for example, here this model uses the viscosity, and the viscosity transport the angular momentum through the disk. So this naturally leads to quasi-Keplerian rotations. So also, for example, here you have the density, the superficial density of the gas in the disk, and you can see that depends on several parameters of mass rate, orbital velocity, and here is the alpha parameter. This parameter gives you the viscosity in the disk. So for example, in a recent work from Rimullo, in 2018, they found this alpha parameter be larger when the disk is in the build up, and then in the dissipation phase, you have a lower value, okay, for the viscosity. So also, if you consider larger disk, then this density profile can be approximated to this power law, okay? So this is an approximation for the density profile, but it works very well. So the power law, you need a base density here. So you need to put a base density and also an n exponent in order to reproduce the density in the disk. Okay, so then the density is going to be expressed by a power law in the radial direction and for a Gaussian profile in the vertical direction. Okay, so many code use this ad hoc parametric model that works very well, and also is faster in computational means. Okay, so what is the aim of the project? The main aim is study a large sample of V star in order to try to seek for correlation between the phase disk and also to the change in the star. So first, to do that, we need to do a lot of observations in the optical and also in the near infrared range. Here I put it in italic because this part is not complete in the project. We just have observation in the optical part. The second point is determine the stellar parameters by fitting stellar model atmospheres to the photometric data and metallic lines. For example, helium 4471, that is very used to obtain the stellar parameters. Then do a statistical study from these measurements. And finally, study the emission line using a radiating transfer code in order to obtain these parameters. Okay, so for the N1, the sample, here we created in 2018 the database VSOS. VSOS means V Star Observation Survey, and it is an open database with 71 V stars that were observed with the same instrument, mid-resolution spectrograph in the optical range. So we try to follow up a spectroscopy of this target. So we have observation from 2012 to 2015. Then we stopped observation because lack of money, but then we could start it again the last year and this year, okay? So the idea is complete for these 71 V stars. a lot of spectroscopic data. So we look for these stars in the VSS database, that is another open database, but has several VS stars observed in the north and southern hemisphere. And also you have several instruments and resolution and wavelength range. So we look for this 71 star in this database, and we complete our VSOS data. Also, we have another catalog that is called Foster, that they are very valuable, important because the observations were made in the 80s. But the only bad thing is that the resolution is very bad, and also we have only one part of the optical range. Okay, anyway, we are evaluating to use or not this database because we have problems to calibrate the data. And now we are observing from, I think, November last year, we started to observation in Casleo, in La Silla, and Las Cumbres Observatory. So these are new observations. We started with the stars that are showing variation first, and then we are going to complete the other stars that are in like more stable disk. So all of these are between mid and high resolution spectrograph, and all of them in the optical range. So what we did first? First, we download the photometric data from Visier. Then we use Kurux and Tlasty model that are stellar model atmospheres. We download the database that is available in the website. So for a star with temperatures higher than 50,000 Kelvin, we use Tlasty because has a non-LTI considerations, but Tlasty doesn't have a lower temperature. So for a star with lower temperature, we use Kurux models. Okay, so using this, we found the best model describing the photometric data, and therefore we found the effective temperature, the gravity, and the stellar radius. So then we use these parameters to find the best Tlasty convoluted by rotation model, and we compare with helium and magnesium 2 lines from the VSOS database. So this is the spectroscopic data. And then we found again a better effective temperature, gravity, and a VCME value. Okay, so then these values, we put it again at the beginning in order to do an iteratively process. Other thing that we did is do measurement on the H-alpha line. So for example, here we measure the equivalent width. So in order to see how changes in time and see if it is in a formation or dissipation phase. Also, we measure the double peak separation in order to have an approximation of the size of the disk in the optical part and the rotation of the disk. Also, we measure the violet to red peak ratio. That remember that this give you information about the overdensity in one part of the disk. And also we measure the radial velocities, not only in H-alpha, also in metallic lines in order to see if there is binary features and non-radiant pulsation. Okay. So here is an example of how works the code that we have. Here in black, we have the spectroscopy data, and in red, we have the model. Okay. So for example, this is the best model for this line, for this star. So here we have the VCNI, the effective temperature, and the effective gravity. For example, if we have more than, usually we have more than one spectrum for a star, so we choose the major absorption in helium line, and this was the spectrum that we modeled. Okay, so we found, in general terms, we found that, for example, almost all stars are rotating between 250 and 350 kilometers per second, and the temperature corresponding to this rotation is between 15 volts and Kelvin and 26 volts and Kelvin that correspond to early to mid spectral types. Okay, and this is the 20% of the sample. Also, in our sample, 13 targets are in not active phase. And I mean, comparing the spectroscopy data also from the other databases. And also the BCME values for this not active phase is lower than 150 kilometers per second, okay? 37% of the sample has a stable disk and more 56% with showing DPS, okay? So this means that you have a double peak separation, so you are looking the system between the pole and the equator. So it's related with inclination angle. And also from this sample, we have 7 targets that show the complete cycle of the formation and dissipation of the disk, and one of them more than one time. So we use these 7 targets to do a follow-up spectroscopy. So these are the main target in the sample. And also now we are modeling the disk using the H-task code. Okay, so this is work in process and we hope to finish this work during this semester. Okay, what we did before with the all other sample. So first we used the BDisk code and B-Ray code that was developed by Aaron Seawood and Carol Jones. So this is a relative transfer code and have a lot of approximation to reproduce the disk, but it works very well. There is a lot of work in the literature that use this code. They create a grid using H-alpha. So the grid was created for different size of the disk, 4 size, and also different inclination from 10 to 90 going in a step of 10 degrees. We have also a range of base density and the n exponent. So for example, in black here, we have the observation and we use a minimization method in order to look for the best model that reproduces the observed line. So here, for example, we have the best 50 models and we use a figure of merit to choose the best models that has a value of figure of merit less than 1.5. So for example, for this star in particular, for this spectrum, we have that these colors represent the best models for the observed line. Okay, so you can see that they're very similar. So each model have different this parameter. In order to find what is the best value, we made an average of these parameters and we construct a plot here for a base density and for the n exponent. So here in this plot, you have the most representative values that we found for all the sample in VISOS. So here, for example, we found lower values for n, 2 and 2.5, for example, and the density is in the order of 10 to the minus 11. So here I put the density profile that we use. So this is the density, base density, and the n exponent. Also in blue, you have the early type stars, and in red the late type stars. Okay, so early we choose between V0 and V3, and the late type between V4 and V9. Okay, so the comparison between both spectral types was that, for example, for the hotter ones, we found that the disks are more massive, and also the specific angular momentum is higher. So this means that the star has a lower rotation, and we should consider that the mechanism should be efficient at low rotations. Okay, and in the case of late B-type stars, we have that the disk is less massive and also the specific angular momentum. Okay, also in our sample, we have a less number of late type stars. Okay, the majority are B2 type. So a recent work that we did was calculate the VCN value for the whole sample in VESOS. So because we have more than 300 spectra in general between all the targets, we decide to create an automatic code to do it. So the code use the Fourier transform method to obtain the VCN value. And the work, you can see it in Solar 2022 that was just published in the last month, I think, I don't remember. So here we choose 8 helium lines, and we calculate the VCN in these H lines. So the method works like this. First, we put the line, we choose the, for example, here is whenever line, I think. So you just choose a line that is represented in black. Then we create a Gaussian fit that is in green. So in green, you have the best Gaussian fit for this line. And then we choose different area. And the area is going to be the spectral window to calculate the VCN using the Fourier transform method. For example, the 3 different area was spectral windows of the standard deviation times 2, 2.5, and 3. So you have less area, a medium, and then more. Okay, why this? Because the Fourier transform is very sensitive to the to the spectral window that you are entering to calculate the VCN value. Okay, so this example is only for 2.5. So in green, you have the best Gaussian fit, and the area that corresponds to this 2.5 standard deviation is represented in blue. Okay, so the blue will be the signal to calculate the VCN. Also, here you have different noise, because depending on the signal to noise, you are going to have different observed line profiles. And these are fake line, for example. So here you have different rotation that was created the line, 200, 300, and 400. So we put 6 criteria in order to choose if the line is good enough to be calculated for this method. So for example, here it is too noisy, and if the rotation is too high, the program cannot recognize the line. So for that reason, doesn't choose the line, for example. So the result, it is here. For example, if the line has a very high signal noise, you are going to find the same rotation that the input of the line. But if you move for very poor signal to noise, then the rotation changes a lot. Not a lot, but changes in comparison with the original line profile. Okay. So in that way, we calculate again the VCN values for all 71 B stars in the VESOS database. And this is an example of 1 star. So you can see that for different helium lines, you are going to obtain different VCN values. Almost all people in the literature use this line, 4471 helium line. And in fact works very well, because in all epochs the VCN is the same. But if you use another helium lines, you are going to obtain different values. So we propose that for VCN calculation, we should use more than 1 line, because you have different values. Here in the box plot, you have the average of the VCN, and in fact is in agreement with the literature, the values in the literature, okay? So other work that we are working on is a FAPES project that is a collaboration between the University of Sao Paulo and Universidad Valparaíso. And the project tried to create the accretion disk, but using wind, okay? So the hypothesis for this project is first that these structures are fed in a manner similar to radiation-driven winds. And second, the rotation of the central star play an important role in the formation of the disk. Okay, so if we have a high rotation and also we have the stellar wind, because it's a massive star, so we have a very strong stellar wind, then we should, or we can create a accretion disk. So we know, for example, that the standard solution of line-driven winds, the theory of line-driven winds, cannot reproduce an outflow with low terminal velocities and with a high mass loss rate. But now we know that there are other solutions for the hydrodynamical equations, like the delta slow solution, for example, and these can give you a slower terminal velocities and also higher mass loss rate. So it's perfect for the accretion disk. So this work only if the star is rotating close or more than 75% of its critical rotation. Okay, so if we have these features in the central star, then we can describe an outflowing disk like wind at the equator of the star. Okay. So here we have the velocity profile, and you can see that the terminal velocity is about 400, so it is okay. And here we have the density profile of the wind. So it's also with values very similar to the other found with the ad hoc parametric model. Okay. Also, we know that there is still too fast in the velocity in the wind. It is still too fast using only the delta slow solution, so we have to add the viscosity. And this is also a recent submitted paper that we sent this month. Okay, so the project is very similar to the, I'm sorry, I have the reference here. No, yeah. So the project is very similar to the work that was did by SILAG in 2014. So they use the VDIS code and they modify the code in order to read the hydrodynamical output with the velocity and density profile calculated with hydrodynamical equations, and they reproduce theoretical H alpha line profiles. Okay, so here we are doing the same, but using the H-task code that it is a 3D Monte Carlo radiative transfer code, and H is come from gas and also can reproduce dust structure. So there is a self-consistent code. It has several options to reproduce a disk. It's not only for B star, it's also for B bracket E stars. So here we have to first create a conversion in order to read the output from height width code in order to reproduce the observed emission line profile. So this is the work that the PhD candidate Amanda Rubio from Universidad de Sao Paulo is doing. So here is an example of how the grid looks. She put, for example, here more solutions in order to put the density from height wind. This is the mu grid. And here we have the preliminary result for this. For example, we have H alpha emission line, and you can see that for lower inclination angles, you see that the profile is very similar to the observed ones, but when you move to higher inclination angles like this, you can see that appears a kind of bumps in the wings of the star. of the line. So this is not usually seen. I mean, we can see a DPS, but not like this. So we are working in what maybe is explanation for this. And one of the explanation maybe is that the conversion grid is not the best for the kind of output in the high winds. So Amanda is working in improve the conversion grid. So this is the recent result from her. For example, she creates a VDD. So this is just a model from HDAS using the ad hoc model to create the disk that is here. And this is the value for the model that is in red. And then she creates a fake density profile in the conversion grid in order to reproduce the same profile in HDAT. And this should be the same because she's using the same profile. But we have some difference when we are looking to the equator, okay? And if you are looking to the pole, the profile is better. So this is working on, we are working on this, but we also hope to have very good result this year. So to finish here, I have a summary and some conclusions. First, the important thing is that we have B star, that they are the only object in the universe that show the accretion disk. Also, we know that there are several futures of the central star that maybe a combination of these futures can give you a decretion disk, but we still don't know what is the mechanism to turn on the mass loss rate. And also we are trying to complete a follow-up spectroscopic for several B star in order to seek for correlation between the features of the star and also the phase of the disk. Okay, so we are still observing and completing the VSOS database. We are still doing measurement of H-alpha line and other metallic lines. We are improving the VCME value by using now another code that consider the change of the geometry of the star due to the fast rotation. And also we are working obtaining the models for the H-alpha line in order to find these parameters using HDAS with two considerations, with a parametric model, with the BTD, and also using the wind model. And that's it. Thanks for listening to me. And if you have any question or if you want to be part of the project, you are very welcome.
Well, thank you very much, Catalina, for your talk. Very interesting. So we have plenty of time for questions. So I would invite people to, you can either raise your hand or you can just unmute and go ahead and ask your questions. I will try and watch for people with their hands raised, Catalina, while you're answering. So yes, if we've got some questions, that would be great.
I should stop to share my screen or not?
Whatever you wish, yeah. And then if you need your screen, you want to show a slide back, if somebody's question relates to one of your slides, you can always start again. Okay. That way people can see each other.
I want to see your face for that.
Okay, well, we've got a couple hands. We've got a couple hands raised. Okay, well, let's start with the first hand in the list I see is Anahai Granada from Argentina. So go ahead, Anahai.
Hello.
Hola, Anaí.
Catalina. Hi. Thanks for your very interesting talk. I have a question on the stable disks you mentioned during your talk. You said that 37% of your sample have this kind of stable disk. Can you comment on the time scale of this stability and how frequently you observe them?
Yeah, for example, I mixed from two databases. I mixed the observation. For example, from VSOS, we have only 3 years, And now we are observing again, but we are working on that. From the BSS database, we have observation from 97. So we have, from 2000 or 97. So we consider that time scale as an stable disk.
Okay, but so you have times where you didn't have any observations and the star could have had some activity, or?
I mean, okay. Yes, one of them, for example, we have very slow variation, like in the peak of the line. You can see, for example, like a third peak that is varying in the line. That kind of variation we consider it as a stable disk because we are looking for the phase for the completed cycle. So we want to see for the dissipation and formation of the disk. So when I mean a stable disk, I mean of that. I mean that there is not changing like the active phase of the B star. Just that.
Okay, thank you. It's you have a developed disk during the whole period, but not completely stable, but long-lasting disk. Okay.
But the disk is present.
Thank you.
You're welcome.
Thanks, Anna. Hi. Okay, the next hand I see, and I'm going to pronounce the name wrong, so I'll apologize in advance. Branquida?
Branquisa.
Yes, hello. Can you hear me?
Yes. I'm sorry if I
Hello,
pronounced the name
Catalina.
wrong.
Hola. Hi.
Thank you very much for the clear presentation. I have one question regarding that determination of the parameters. As far as I understood, you use some helium lines and H-alpha lines once you model that. Did you try also to maybe fit spectral energy distribution of those objects which you analyze? Because I'm wondering what can be the uncertainties in your determination of these parameters if you use only some particular lines.
The code that we create do two parts. The first part is with the photometric data. So we download the data from the VCR database, like here, for example. So these in the red triangle are from the VCR. And then we use the stellar model atmosphere that can be Kurux or Clasty, and we obtain the stellar parameters. But we know that this is not like the only method to obtain them. So the second part was use spectroscopy data and use the same values, but then try to find the best only for the spectroscopy data and compare both photometric and spectroscopy parts. That was the way.
Thank you. Did you maybe one more question about that mechanism which can drive that creation of disk? Did you maybe consider that low metallicity stars can be that all these objects you use? I suppose that you use solar metallicity when you analyze those stars. Can it happen that this star can have a little bit different metallicity?
Of course,
because
but no,
in low metallicity stars, when they rotate fast.
I mean, for example, like the hot theory that explains the formation of the disk can be, for example, a combination of binary. So maybe all B star are binary, and for that reason they rotate very fast, and the rotation of the star, because you have different geometries, so that in the equator you are going to have less gravity, and if you have less gravity and another mechanism that push material from the photosphere of the star, then you can create a disk. So maybe it's rotation and non-radiant pulsation, or also binary stars. But now with Michelle, we are working in trying to explain the disk, but only using a stellar wind. So there is a lot of different theories to try to explain it.
Understand. Yeah, thank you.
Yeah, you're welcome.
Okay. I see Doug Guys has got his hand up, so you can go ahead and unmute Doug and please ask your question.
Hi, good morning. Very nice talk. Thank you so much for telling us about your wonderful work, Catalina. I had one comment and then I had one question, so if you'll indulge me. The comment was about using the Fourier transform method, and you described it very well in your talk and about the effect of signal to noise and how that will affect your results. And I wanted just to add to that that there's two aspects on the theory side that that could cause some systematic errors. One is the fact that the stars are rotating and are probably experiencing gravity darkening, so that their equators will appear darker than the poles, and consequently the line components that come from the equator will be less representative, or less represented, less weighted in the final flux profile that you observe than would be the case if there was no gravity darkening. And so I think this has been known for quite a while, going back to a paper by Rich Townsend back in '87. But the point is that that will cause a systematic effect that you will tend to underestimate.
Yeah.
And the second point about the Fourier transform is that it assumes that the intensity profile that is coming from the surface is the same whether at the center of the star or over at the limb of the star. But if you actually look at real intensity profiles, for example, that you can calculate with SynSpec, the program that comes with T-Lusty, you can actually see what these profiles look like as you go from the center to the edge. And invariably what you find is that the actual profiles, at least normalized to the continuum, are weaker at the limb than they are at the center. And so again, that I think will introduce a systematic effect that will tend to actually underestimate the true rotational velocities. So anyway, that was one thing I wanted to put out there, sort of something to be aware of at least. It's going to be most important for the most rapid rotators, less important for the moderate rotators, but nevertheless, it is a systematic effect. So
Yeah.
it could have some issue. The question I wanted to ask, and to a totally different subject, you mentioned about measuring the VNR peaks in the H alpha, and I was just wondering, have you found cases where the VNR actually show cyclic variations, where you've been able to get a full cycle of a V over R, where V is bigger, then R is bigger, and then V is bigger? Thank you.
I'm sorry, I didn't understand the question.
So he asked if in your measurements of the V over R ratios, if you've found a star that goes through a complete cycle where the V is greater and then gradually the R is greater and then back to the V peak.
Yeah, in fact, I want to answer also the first comment.
Okay,
yeah,
go ahead.
We realized that we know that we have to consider the gravity effect also. So now we are working with the spectra code. That is the code that use Levenhagen in the paper of, I can remember the years of the paper, but he used the Tlasty models, but he convoluted, he considered the change in the geometry. So they have the gravity effect and also different laws for the limb darkening. So we are using that code, and our idea is to put the same automatical way to reproduce to calculate the VCME, but with this new code. Michelle, I know you have the years of the paper.
I put it in the chat, 2014.
Okay. 2014, thank you. And the other things, in our sample, in fact, almost all stars has the double peak separation. So I don't have the percentage now, but yes, we have a lot of them that show the complete cycle of the VR chains. So the change, in fact, sometimes is less than 3 months, for example. So because we have observation only in 3 years, yes, we can have the complete cycle on the period of that.
Thank you very much.
You're welcome.
Thank you, Doug. Okay, I see Dietrich, you've got your hand up, so please unmute and go ahead and ask your question.
Yeah, very interesting, very exciting project. Thank you very much for sharing your your preview. How often, at what cadence can you observe the VE stars? And would it be possible for you to pick stars when they're being observed by TESS and then observe the stars that are in the field of view of TESS, say 3 times a night, every night?
Yeah, yeah.
Because I think that would be the most decisive data set to distinguish between winds, which probably are a relatively steady process in spite of their instabilities, and mass loss events, which might be triggered by the superposition of many non-radial pulsation modes.
Yeah, in fact, I forgot to mention that we are observing from the last semester, from the last year, with a project with Jonathan Lavadier. I don't know if Jonathan is here, but the idea is to observe at same time that TESS is observing B star. We are getting observation from the ground with this telescope of Las Cumbres, that you have 4 telescopes that are for all part of the world that have a high resolution. So the idea is to observe at the same time that TESS is doing it with the observations, with the optical part. And the hypothesis is that if we have change in the light curve with TESS, then we should see the change in the H alpha line, but not at the same time. In fact, usually you see first the change like a outburst in the light curve, and then you will see a change in the disk. So if we can try to measure like the days from the difference between one and the other, maybe we can see if this is the reason for the formation of the disk, for example. So this is a project that we are working on with John, and we have data right now, but we are still in work in progress. We are in a lot of projects right now, in fact.
Yeah, I'm collaborating with John, so I'm aware of the reasoning. My question is whether with your facilities in Chile, you can contribute spectra at a high cadence.
Yeah, we can do it because, for example, all the money that I didn't use the 2 first years for the conference and that kind of stuff because the pandemic situation, we bought time. So we have time in the north of Chile, in Antofagasta, no, in La Silla, and also we have time here in Santiago. Maybe they are not the best part to observe because the weather, but we have all the time that we want. I mean, I can observe whatever I want in that telescope, so that is very good.
So these would be stars in the constellation Corona Australis.
Yeah.
Thank you. Best of luck.
Okay, I see we have one more question from Tonis. And I apologize if Tonis, I haven't pronounced your name right, but go ahead and ask your question.
Hello, that's fine. Hello, Catalina. Thanks for a very nice talk. I have a question about analysis of metal lines, metal emissions, and maybe also helium emission. Have you thought about using them to get more information about the disk dynamics and properties?
We observe some emission lines like helium. I forgot how to say fierro in English.
Iron.
Iron, thank you. So we have some emission lines of iron, but we only have a measurement on the line. I mean, we can measure the equivalent width or something more, but only in the line, because we don't have a radiative transfer code, for example, to obtain emission in metallic lines. So.
Okay. Mm-hmm.
In particular, I am not working in that part, for example, just analyzing the complete cycle of a B stars.
Mm-hmm.
But thank you. I will consider it. Thank you.
Okay, we're starting to run short of time, but we do have I'll let hopefully, is it Leonter? Go ahead and ask your question. And then Michelle has one as well. So then we'll try and wrap up because it is, I think we are at 10 o'clock.
Hello, Catalina. Thank you for your talk. Very interesting. Now, my question is in your slide 18. So you chose the parameters of the disk, and you make a distinction between early and late stars. And we can see that they are in different parts of the plot. So why we observe this?
Why I select just one part of the parameters?
No, for example, you can see that early are more to the lower left, while late are in the on the right. So more. So why we observe this distinction?
Why, for example, you have more late star here and
Yes,
more
in that
early?
that while blue are more in the left part of the diagram.
Yeah, it is like very observed that, for example, early type star that are hotter has more massive disk. And so if you have more massive disk, you will have a base density higher, for example. So for that reason, you have values more early type here in that part of the plot. And in the case of late type, you have the mass of the disk is less. So you will have n values higher. And that should be the answer. But also you can see that there is a mix here. For example, here in this part where the parameters are more representative, you have both early and late. So maybe there is another explanation for that also.
Okay, yes, thank you.
Okay, Michelle, go ahead.
No, just one comment. You in your introduction, Carol, you said that Catalina created the BESOS database.
Besos.
Yeah. And in Spanish, that read besos and means kisses for you all.
Oh,
So
sorry about that.
that is the second aspect of the database. That's all what I said. I want to say to you.
Okay, thank you. So thank you very much, Catalina, for a very nice talk. I just have one follow-up question that relates to one of Doug's questions. If you've got lots of stars with those V over R variations, once you've got your data up and your collection going again, it would be really interesting to see what the periods are for that range of, if you have lots of them, it would be very interesting to see what kind of overall periods you have for those complete cycles. I would definitely be very interested in that. So thank you again. That was a very interesting talk. And thank you for everybody for coming. So we'll see you in another month. We have another talk coming up on on BE X-ray stars, and I will circulate the abstract and details a little bit later. So thank you very much, Catalina.
Okay, thank you, Carol, for the invitation. Have a nice day. Ciao.
Thank you. Take care.